So we are looking at, is it recording? Yes, it's recording. So I'm looking at this function. It's polynomial, the domain all real numbers. But I will have to determine the limit x approaches negative infinity from negative 2x cubed plus 3x squared plus 36. And then, of course, when x approaches infinity. So we know the answer. Because when I plug in only in the most powerful one, negative infinity, I get infinity. And when I plug in infinity in the most powerful one, I get negative infinity. So that would be my starting point. X, f prime of x, f of x, and f double prime. What I have already is this, and I have that the end behavior is infinity and negative infinity. I will determine the x and y intercepts, because first I have to exhaust the function. We didn't do this before because we didn't have to graph, but now we're also asked to graph. So I need to determine the and behavior, which we did. We need to determine the x-intercepts, which means f of x equals 0. Since it's degree 3, I hope for 3 solutions. So negative 2x cubed plus 3x squared plus 36x equals 0. Yes, I will divide both sides by negative 1. And I get x cubed minus 3x squared minus 36x equals 0. I will definitely factor out x and get x squared minus 3x minus 36 equals 0. As I said, I expect 3 solutions. One of them is 0. And the other 2 will come from x squared minus 3x minus 36 equals 0. Quadratic formula. Negative b plus or minus b squared minus 4 times a, which is 1, times c, which is negative, so I prefer doing this, over 2a. I'll put it in the graphing calculator. Parentheses for the top, remember the numerator, 3 plus the square root, in parentheses, 9 plus 4 times 36. Close the parenthesis inside, go outside for the other set of parentheses and divide by 2. And I need the other one as well, in which I override the plus. And negative 4.6. So I'm going to say x approximately 7.7, x approximately negative 4.7. Go to the table. 0 also in the table because I have to find the y-intercept, but it turns out that it's 0. And then 7.7, it's also 0. And then negative 4.7 is also 0. I can't find anything about the function anymore. I found everything that I could from the function itself. So I have the end behavior, and I have the x and y intercepts. That's done. Now I have to go back to the first derivative. How I can continue, and then I'll look at the second derivative. Let's see what we get. So function, where are you function? I have it here, actually. So f prime, negative 6x squared plus 6x plus 36. I'm looking for critical numbers now. They cannot come from f prime of x being undefined. That's not possible for a polynomial. But they may come from f prime being 0. So this is for critical numbers. And then negative 6x squared plus 6x plus 36 equals 0. Of course, I will simplify it as much as possible, dividing both sides by negative 6. I like this. X minus 3x plus 2. So we found two critical numbers, x equals 3 and x equals -2. It's getting crowded in my table, so I'm going to use a different color, -2, 0, and 3, 0. Yes, now I have to study the sign, not a problem. I know it's a quadratic function with a negative leading coefficient. It has a maximum. I can plug in 0, I get positive, and of course negative. At this point, I stop and make sure that these two rows make sense. Not before I find this value and this value though. So let's do just that. So where's my function? I have it. Okay, here it is. In this function in the graphing calculator, I will plug in -2 and 3. Because I'm going to graph it at the end with the graphing calculator anyway, so I should have it in there. So let's plug it in. -2x to the third. Nobody's stopping me, so I don't know. I'm hoping that you're following. Plus 36x. I go to second and table, and I plug in -2 and 3, and I got -44, and I got 81. Okay. So now I have to make sure that these two rows work well together. And now this is the moment of truth when I catch my mistakes. So let's take a look. From positive infinity to 0 and to -44, the function is decreasing, and that is exactly what I see there. From -44 to 0 to 81, yes, it's increasing, and that's exactly what the first derivative is telling me. From 81 to 0 to -infinity, the function is decreasing, and that's exactly what the first derivative is telling us. So we are okay. Finally, I have to study the second derivative. Look at all this work. If I don't summarize the information, I'll never be able to graph anything. Okay, so let's take a look at the second derivative. Here's the first derivative. Here the second derivative will be -12x plus 6. When I set the second derivative equal to 0, I get that -12x plus 6 is 0, or x equals 6 divided by 12, or x equals 1/2. Of course, there must be something in there where I have to squeeze it in, right? Okay, so the second derivative is a linear function with a negative slope. It's coming from positive going to negative. So I already studied the sign. I know that this is the case. And I have to plug in 1/2 in the graphing calculator to determine. So second, and I 1.5. And with 0.5, I get 18.5. Sorry. 18.5. At this point, I'm ready to identify points, max, min, inflection. So I see that -2, -44 is a local minimum. I see that 0, 0 is nothing other than the an x-intercept and y-intercept. But I see that 0.5, 18.5, because the second derivative changes sign, this point must be an inflection point. Then 3, 81, because the first derivative changes sign from positive to negative, this is a local max. This is nothing, it's just an x-intercept. And we're done. Now we have to put everything now in, using everything we are ready to graph. So I'm having some difficulties here with 81 and 44, -44. So I'm going to use a different unit for the y-axis than for the x-axis because of these big numbers. Questions? Please say something. Anyone, please? Anyone there? I hope you're there.
Yes.
Thank you, thank you. Okay. So I'm going to plot negative 4.7, so roughly negative 5, 0. I'm going to plot negative 0, 0. I'm going to plot 7.7, roughly 8, 0. 1, 2, 3, 4, 5, 6, 7, 8. So I have the x-intercepts. Negative 2, negative 44. I'm going to say 10, 20, 30, 40, 50 is here. So this is negative 50. Then I have 0.5, 18.5. So 10, 20, so 0.5, 18.5, somewhere here. And then finally 3, 81. 1, 2, 3, this is 3, 81, 10, 20, 30, 40, 50, 60, 80, 90, 81. So I plotted all the points, 3 x-intercepts, 1 local min, 1 local max, 1 inflection point, and 1 local max. I know the function is coming from positive infinity somewhere here, and it has to go to negative infinity somewhere here. And now we put everything together at this point. Let's graph. I need some other color. I don't know if you can see this one. Let's try. Okay. Oh, I think the silver is good. Okay. Opening up, decreasing from infinity to the x-intercept. Opening up from positive infinity to the x-intercept. Continuing to decrease, still opening up to negative 2, whatever. So I don't like it because this is a smooth continuous function. I can't twist my wrist. If I twist my wrist, then it's not working. It's not good. Okay. Perfect. So it's decreasing, crossing at negative 4.70 and reaching negative 2, negative 44, where it's a local minimum. Still increasing, now increasing, still opening up to the origin. Fine. And the origin continues to increase to 0.5, 18.5. So local min. At this point, it changes concavity, and all the way will be opening downward. It continues to increase to the local max. Changing concavity here, which is the inflection point, local max. At this point, starts decreasing from the local max, crossing at 7.70, always opening downward, going to negative infinity. I can put that away now. So this is our function f of x. Of course, I forgot what it was. Negative 2x cubed. What was it? Plus 3x squared and plus 36x. Am I recording? I am. So in case you want to see this with the graphing calculator, I assure you the graphing calculator will not tell you where the inflection point is, but you know what it is. So here's the function that we had, and obviously I have to change the viewing window. The function goes to negative 44 and it goes up to 81. So the viewing window now is very clear. Between, I can choose negative 10, 10, that's okay. Scale of 1, it's okay. Y minimum, definitely negative 50. Y maximum, definitely, let's say 90. And with a scale of 10. And I expect a perfect graph, but the graph will not tell me where the function has the inflection point. I know where it is. We know where it is. At 0.5, comma 0.5, comma 18.5. But the calculator will not tell us. Any questions? Any questions on this? So this is our first application in this chapter. So I did not write them last time. I'm going to write, so there are 3 applications in this chapter. One is graphing. Exactly what we just did. Number 2 is optimization. Number 3, Newton's method. And that will be the end of chapter 3. Yes, there are a few things in there that we will discuss, like L'Hopital's rule, which we know. But we haven't looked at sophisticated situations with all possible indeterminate cases. So that will be the next section, 4.4. But we haven't finished, of course. We still have to practice. Now, section 4.5 is exactly what we just did. We put everything together, but I'm not ever waiting till section 4.5 to graph. I can't do that. So 4.5 is a summary of everything we've done in this chapter. 4.6 is graphing with calculators. We do that all the time. So I'm not going to test you anything on 4.6. And 4.7 is optimization. 4.8 is Newton's method. What would you like me to continue with? I don't want to start 4.4. Not because we have 15 minutes left. It's because I consider that we still have to practice this. Any questions on how we graph this function? Anyone? Anything? So we still have to look at rational functions. We only graph the polynomial function. So we still have work to do. And I have not mentioned anything about the second derivative test, but I like to mention something. We know what the first derivative test is. So here is the idea about the second derivative test. Well, what is it all about? I'm going to do this. Do not correct anything. I'm going to put this back in. Nothing is wrong. Don't change anything. I just want to make a point. Okay. So let's talk about the second derivative test. Second derivative test. Let's take a look at this situation that we just looked at, right? We graph this function. I don't want this to show, and I don't understand why it still shows, but I'll try again. Okay. So let's suppose I never use this, and I would not force you to. It's up to you. You choose what you like. So let's suppose we decide not to study the sign of the first derivative before we find the second one. But we still have to find the critical numbers. So we have two critical numbers, -2 and 3. We know that the derivative is 0 there, or maybe undefined, it doesn't matter, but we know that these are the critical numbers. The derivative is 0 there in this case. We reach the second derivative. We find that the sign of the second derivative is what you see here, positive and negative. So there is a critical number where the second derivative is positive. What type of point could that be? So there is a critical number in the territory where the second derivative is positive. What kind of point will -2, -4 be? It can only be a minimum. If it is a minimum, then I know for sure that this sign here is negative and then positive. Similarly on the other side, there is a critical number and the second derivative is negative. So then this critical number, 3, 0, can only be a local max. If it is a local max, then the signs of the first derivative must be positive and then negative. The reason this is, and I'm going to put it in writing for you. So the reason why I don't use this is because by the time I get to the second derivative, I may already have a mistake, either in the first derivative or who knows in the limits, who knows. I don't want to wait to discover my mistakes when I'm already finished the problem with the second derivative. So I want to study the sign of the first derivative, make sure that these two rows work well together, and only then I study the second derivative. Now I can check with the second derivative test and say, okay, so if the function opens up, this must be a minimum and the signs have to be those. True, correct. Okay, now it's opening downward and it's a critical number somewhere in there, so the signs of the first derivative must be these, because it must be a maximum. Yes, but to wait till the end, till I'm done with the second derivative, to go back and study the sign of the first, I will not do that. I can't. It's too late to find mistakes. I have to start from scratch. So, again, as the second derivative test, I'm going to write this. The second derivative is positive. And in that territory, f prime is 0. Then there is, this point is a maximum. F has a max, has a min. Because when the second derivative is positive, the function is concave up. When the second derivative is less than 0, and at that point, somewhere in that interval, the first derivative is 0, which means there is a critical number. That critical number changes into f has a max. This is what the second derivative test is saying. I don't recommend using it unless you want to check at the very end. It's up to you. It's very acceptable if you decide to use it. But I truly believe that getting to the second derivative without studying the first derivative, it could be risky. Okay, well, we have 10 minutes left. What would you like to do now? Anything. Anything? Anyone? I don't recommend these tables. They're very hard to read. I recommend use mine or invent your own, because I think that this is difficult to read. Any questions for me? Anyone? Anyone? No one has any questions, anything?
Can we just do another problem?
Yes, yes. Yes, any preference? Should I just, maybe we should just look at a rational function, a simple one. How is that?
Yeah, I think a simple one sounds great.
Okay. I know. These problems require a lot of attention. Okay, I'm just looking, I'm at 17, 18, no, oh, wow, I'm only 15. Okay, so let's say f of x equals x minus 1 over x plus 2. Well, this is a rational function, and I already know a few things about it, that x cannot be negative 2. I already know that the limit as x approaches infinity from x minus 1 over x plus 2 is infinity over infinity, and I will use L'Hopital's rule. So this is limit as x approaches infinity from 1 over 1, which is 1. And that will not change for negative infinity. And we've done this a long time ago. Y equals 1 is a horizontal asymptote. I also know that x, we had a problem like this on the last test. So x cannot be negative 2, which means x equals negative 2 will be a vertical asymptote. So I have to find the limits left and right. So limit as x approaches negative 2 from the left, and limit as x approaches negative 2 from the right of f of x. These are the preliminaries right away. And I also have to find f of 0. That f of 0 will be negative 1/2, which is the y-intercept. And also f of x equals 0, which will give us x equals 1. That's the x-intercept. Okay, so negative 2 from the left. The numerator will be negative. The denominator will be 0. Again, the same thing, negative 2 from the right, negative over 0. So negative 2.1 will make the denominator negative, so the answer will be positive. With negative 1.9, the numerator is negative, the denominator is positive, so this is negative infinity. These I have to determine quickly before I even start the table. Sorry. So let's see what I know. I know that the limits at infinity, 1. I make myself a note, y equals 1 horizontal asymptote. I make myself a note that negative 2 is a vertical asymptote. I have limits left and right, infinity and negative infinity. When x is 0, I have a negative 1/2. When x is 1, I have 0. I exhausted the function. I have the end behavior, I have x and y intercepts, and I have what happens next to the vertical asymptote. My next step is the first derivative. And study the sign of the first derivative. So f prime, it's a quotient. The top prime is 1 times the denominator, minus the top, in parentheses, times the denominator prime, which is 1, over x plus 2 squared. Nice, because x plus 2 minus x plus 1 over x plus 2 squared is 3 over x plus 2 squared. Never 0. Never undefined. Never undefined. Always positive. Nice. Which means the function must be always doing what?
Increasing.
Excellent. From 1 to infinity, correct. From negative infinity to negative 1 to 0 to 1, all correct. Final step, the second derivative. This. I'm going to differentiate this to get the second derivative. Negative 6, x plus 2 to negative 3 times the inner function prime, which is 1. Negative 6 over x plus 2 cubed. Never 0. However, for studying the sign, I will write this. Because this is always positive. And I don't want to waste my time with it. So, when x is less than negative 2, on this side, like negative 3, negative with minus in front. On this side, like 0, negative. Problem is done. We just have to graph it. When we graph functions with asymptotes, we have to start by graphing the asymptotes. There is a horizontal asymptote at 1. And there is a vertical asymptote at negative 2. We do have 2 points, 0 for x, negative 1/2 for y, and 1, 0. From 1, increasing to infinity on the left-hand side of the vertical asymptote, opening upward. Very clear. On the other side of the right of the vertical asymptote, from negative infinity, crossing at negative 0, negative 1/2, crossing at 1, 0, going towards 1, all increasing and all opening downward. Never changes concavity. So this is function x minus 1 over x plus 2. Questions?